Section 3.6 is about a procedure called L'Hopital's rule. It's named after a French mathematician whose name is L'Hopital, and somewhere around the 1600s or so. And it is used to evaluate limits of indeterminate form. And you might be wondering why we would be going back to limits right now. But as you see, it's going to involve derivatives, which is why we had to do derivatives first before we could talk about L'Hopital's rule. It is important that you understand when you're allowed to use it, so you have to recognize when the rule applies. And also on the AP exam, it's very particular as to what you need to show in order to get credit for it on the AP exam, so we're going to go over that as well. Let's take a look at what L'Hopital's rule says. If you are evaluating a limit and you end up with this indeterminate form, 0 over 0 or infinity over infinity, we had learned some ways of handling this. We had done factoring, we had done conjugates, we had done simplifying complex fractions. This is going to give us another tool for evaluating limits in that indeterminate form, and it's actually very simple. All it says is if you end up with that indeterminate form of 0 over 0 or infinity over infinity, then the limit as x approaches c of f over g is the same answer as the limit is x approaches c of f prime over g prime. In other words, we just do the derivative of the numerator and the derivative of the denominator and then evaluate that limit. So just remember, even though this has the appearance of a quotient, we are not doing a quotient rule. We are strictly just doing two separate derivatives and then retrying our substitution. In this next part, I've got the steps that you need to show in order to receive credit on the AP exam. And when I do the examples, I'm going to follow what this says. So to receive credit, you have to follow these 3 steps, and we will do that as we do our examples. And one thing and I've got it in this box over here, that's important to realize is it is incorrect to say a limit equals 0 over 0. Technically, that is not a correct way of writing that, and we'll talk about that as we move on. The first thing that we're going to look at is how do you know when you're allowed to apply L'Hopital's rule, because you can't just apply it all the time. And that's what this first question is asking me. Should you apply L'Hopital's rule in question number 1? It is incorrect just to say equals 0 over 0. So what you want to show is the limit as x approaches 3 of the numerator and of the denominator is 2 separate limit statements. My limit statements would look like this, and notice I did not get 0 over 0. I got a 0 for the numerator and a 1 for the denominator, which means L'Hopital's rule cannot be applied in A. When I go to part B, I'm going to start the same way. I'm going to do 2 separate limit statements. And here I do get a 0 in the numerator and a 0 in the denominator, which means L'Hopital's rule is going to apply for part B. So now that we've decided we can use L'Hopital's rule in part B, let's see what it looks like when we actually apply it. And realize that we have done problems like this in the past. The way you probably would have approached this is you do the direct substitution mentally, you get the 0 over 0, and then you would factor that numerator and that denominator. And it would look something like this, and there's nothing wrong with doing it this way. It gives me the right answer. Using L'Hopital's rule, I'm going to work the same problem. So I'm going to start like we started in 1b by finding the limit of the numerator and of the denominator. I do that first to verify my 0 over 0, and then I write this statement. And my statement says this limit produces the indeterminate form 0 over 0, so L'Hopital's rule applies. You can use that just as a script. You're going to see every example that I do is going to start doing these 3 steps, finding the limit of the numerator, the limit of the denominator, and then making this statement, and now I'm going to use L'Hopital's rule. And my next step is to start with the original limit and say that that's going to equal the limit as x approaches 3 of the derivative of the numerator, which was just a power rule, and the derivative of the denominator, which is just 1. And now from this limit, I'm going to do a direct substitution by plugging that 3 in. And when I do that, I get an answer of 8. And notice that matches the answer that I got doing it the factoring way. So why would you want to do all of this when you could simply just do what I have in the box over here? And the answer is you may not want to. You have a choice as to the method that you use. So if factoring is what you want to do, then just use factoring. Some problems you won't have an option whether you can use this, and it's very powerful in that it can be used anytime you end up with that 0 over 0. Let's go ahead and take a look at another example. In question number 3, we had done this previously, and we had either done a difference of 2 cubes factoring situation, or you could have divided it out using synthetic division, and I'm going to give you a third option in using L'Hopital's rule for this one. And again, here's that same statement. This limit produces the indeterminate form of 0 over 0, so L'Hopital's rule applies, and now I'm actually going to apply it. The next step is my L'Hopital's in action, so I write my original problem equals the limit as x approaches 2 of the derivative of the numerator and the derivative of the denominator, and then I evaluate that limit by direct substitution, so I plug my 2 in, and I get my final answer of 12. Pretty sure we've done this problem in the past. You can go back and verify that that is the same answer that we got using a different method. Our next example, we also had another method for doing this one, but we'll take a look at what this looks like using L'Hopital's rule here. So again, the first thing I'm going to do is show that I'm allowed to use L'Hopital's rule by finding the limit of the numerator and the limit of the denominator as two separate limit statements. And once I verify, I get the 0 in the numerator and the 0 in the denominator, I write my little script. Here I'm acknowledging that I'm getting that indeterminate form of 0 over 0, so I'm going to use L'Hopital's rule, and now I show the application of it. I start with my original problem as it was given to me, and then I show the limit as x approaches 0 of the derivative of the numerator and denominator. And don't forget to use a chain rule when you're doing that derivative of the numerator. The derivative of sine is cosine. We leave the inside alone, the 5x, times an extra 5. So times the 5 is why our 3 turned into a 15. And now that I've done that, I'm ready to do my direct substitution by plugging a 0 in. Cosine of 0 is 1, so my numerator is going to be 15. And in my denominator, I have 2 minus 0, which is just 2. And my final answer is 15 halves. And again, realize it's not all about the answer. It's about all this work that you show. These limits shown separately, this statement saying I'm allowed to use L'Hopital's rule, and then the actual application of L'Hopital's rule to arrive at that answer. On those first 3 examples, you had some options as to how you could evaluate that limit. On number 5, L'Hopital's rule is your only option for this one. Just running through that process again, I'm going to do the limits of the numerator and denominator as 2 separate statements. And then I say in writing that I get that indeterminate form 0 over 0, and I mention L'Hopital's rule by name, and then I'm going to use it. This is my original problem written out. And then my derivatives, a natural log derivative is 1 over the 2x times the derivative of 2x, and that's the times 2. And my exponential derivative, I write down exactly what I see, which is e raised to the 2x minus 1, times derivative of the exponent part, which is the times 2, and the minus 1 just drops off. And I'm going to clean this up just a little bit. I guess I can cancel out those 2's. And now I'm ready to plug in my 1/2 in for the x. So 3 divided by 1/2 is 3 times 2, so that's going to give me a 6. And substituting a 1/2 into the denominator is going to make that exponent a 0, and e to the 0 is 1. And then 1 times 2 is going to give me 2. And then just dividing that out gives me a final answer of 3. And again, this is just a procedure that you're following to evaluate this limit. And it's a nice application of all those derivatives that we've been learning over the past 2 units. And just like with example number 5, in example number 6, you have no choice but to use L'Hopital's rule for this question right here. And I'm just going to follow the same steps that I've used before. When I use direct substitution on my numerator limit, I plug in the 1 and I get f of 1, and I look in f of 1 is 10, and the 10 minus 10 is my 0, and then my direct substitution in that denominator also gives me a 0. And then my statement saying I'm getting an indeterminate form, so I'm going to use L'Hopital's rule, and now I'm going to write down my original problem and find the derivative. Make sure on that numerator's derivative that you follow the chain rule on this part. This is f of 3x minus 2, so that 3x minus 2 is your inside function. So following the chain rule, I do the derivative of the outside, which is f prime, leave the inside alone, so it's just a 3x minus 2, times derivative of the inside. And the derivative of 3x minus 2 is times 3. And my minus 10 just drops off, and that denominator's derivative is pretty straightforward. It's just a 3. And you could simplify this before you evaluate that limit by crossing those 3's out, or you don't have to. You could do it either way. Either simplify and then do the limit, or you can do the limit and then simplify. That choice is up to you. So I'm going to go ahead and simplify and then plug my 1 in. And plugging my 1 in gives me f prime of 3 minus 2, which is just f prime of 1. And in my table, I see that f prime of 1 is negative 3. So my answer here is simply negative 3. And our last example here is going to show you how to use L'Hopital's if your information is given to you as a graph. But we're going to start it like we did all the other ones, a separate limit for the numerator and for the denominator. When I plug my 3 into my function here for my x's, I get 3 times f of 7 minus 15. And when I look on this graph, f of 7, so this is the graph of f right here. So f of 7 is going to give me a value of 5. And my 15 minus 15 gives me 0 in my numerator. And then plugging my 3 into my denominator leads me to 18 minus 18, which is also 0. So I verified that I got my 0 over 0, and I make my statement. And now I'm ready to do my derivative. And again, make sure you see the chain rule that's going on in this numerator. So that 2x plus 1 is an inside function. I do derivative of the outside, so that's the f prime. Leave the inside alone, so 2x plus 1 times derivative of the inside. And the derivative of 2x is this times 2. And my derivative of 5x is just the 5, and that denominator is a simple power rule. So I'm ready to do my direct substitution. When I go to evaluate f prime of 7, since I'm looking at a graph of f, the way I interpret f prime is I want the slope of f at x equals 7. So I take a look here, and this is linear right here, so I have a constant slope. So I just track my movements from one point on this line to another. So it looks like from here I would go up 2 over 1, up 2 over 1. So it looks like my slope is a 2. And finishing out that evaluation gives me an answer of 7 over 6. And that's about it for L'Hopital's rule. It's pretty basic to follow. You just have to remember all the requirements and all the work that they want you to show for these problems so that you show an in-depth understanding of what you're doing and why you're doing it.